this talk is titled The Need for Accelerated Computing, but really it's going to be a little bit more broad from that. My goal here today is to give you an understanding of what kind of company NVIDIA is, how we became so dominant in the AI and HPC market, and then give you a little bit of pointer on where we see the market moving forward. Now, not a lot of people understand what kind of company NVIDIA is, right? If you're a gamer, then you think of NVIDIA as a gaming company. If you're at one of the national labs, you may think of NVIDIA as a scientific computing company. If you're an AI researcher, you think of NVIDIA as an AI company. And the reality is none of those are true. NVIDIA is an accelerated computing platform company. We have a platform that encompasses both hardware but also, more importantly, the software required for accelerated computing. Now, what is accelerated computing? Accelerated computing is using compute accelerators to solve problems that normal computers can't, that regular CPUs can't in a reasonable amount of time. And there are a wide range of accelerators out there. NVIDIA is not the only one who makes them. On the low end of the accelerator side, you have things like FPGAs, field programmable gate arrays. And then on the highest end of the side, you have the NVIDIA GPUs. And then, of course, the biggest and baddest on the market today is the A100 GPU. But what is a GPU and what makes it so powerful for accelerated computing? Now, at this point, I could sit here and try to explain to you how a CPU processes data serially, one at a time, and how a GPU processes data in parallel, solving multiple problems simultaneously. But I'll never do as good a job as the Mythbusters guys did when they presented at our GTC conference a couple years ago. And if you were at the 2019 conference, I opened with this video there as well. But they came to our conference and they just gave a really great visual explanation of the difference between a CPU and a GPU. So I'm going to turn it over to them right now. If you could hit play in the back. Hopefully we've got sound. If not... No, we don't. Okay, so this is the Mythbusters guys. This is Leonardo, and he is going to paint a picture for you in the way that a CPU would paint. Here we go. All right, so this is a CPU painting a picture serially. And it's not very fast, it's not very pretty, but eventually it kind of gets the job done.
Ladies and gentlemen, Leonardo.
And this is a GPU. This is how a GPU would paint a picture.
3, 2, 1.
In parallel.
Ladies and gentlemen, science class is now over.
That is how you want to run your simulation. And yes, it's a little tongue-in-cheek, but not by much. I mean, today's more powerful mainstream CPUs have anywhere from 12 to 16 cores. So you could think of that as a 16-lane highway to send your data through. That A100 GPU over there has over 8,000. So you go from a 16-lane highway to an 8,000-lane highway, and you really just open up the types of problems that you're able to solve. Now, this is one view of NVIDIA's platform. I don't really like this view, but I do like it because it kind of shows the three main pillars that accelerated computing by NVIDIA is making a difference. The first one and the original one is in high-performance computing. We created the GPU for the parallel processing originally for video games. In the early 2000s, our CEO, Jensen, had the idea of, we've got this really powerful processor. It's able to solve all of these math problems simultaneously. We designed it to solve for pixel color simultaneously. What if we created a library that allowed scientists and researchers to tap into that parallel processing power to solve whatever math problems they want to solve, not pixel color? And so we came out with the CUDA programming language in 2006, and that really kickstarted our entrance into the high-performance computing market. Today we've got a wide range of HPC applications, including Barracuda, that leverage parallel processing. In 2012, there's this Canadian PhD student named Alex Krasinski, and he was the first one to leverage an NVIDIA GPU, neural networks, and a large label data set to train an AI model. He called it AlexNet. This was in 2012. Completely blew the lid off the entire AI and deep learning industry. I mean, it is called the big bang of AI because he was the first one to do it. I mean, it even took NVIDIA by storm or by surprise in 2012. But we saw the opportunity. We doubled down on it. Thankfully, we had already had multiple years of investing in the CUDA programming language. That put us in a really good position to accelerate the rapidly expanding AI ecosystem. And then the third one is the new Omniverse capabilities. Zuckerberg made it really famous by calling it the metaverse. His metaverse is really built on the NVIDIA Omniverse, and it's useful for things other than social media. It's useful really for things like collaborative design. You know, if you are BMW and you've got people designing the tires, people designing the car seats, the airflow. In the past, they were all using disparate design applications, and they couldn't see what the others were doing in real time. Omniverse allows all of these different design applications to be moved under one roof, and so in real time, you're able to add design functionalities and see what everybody else is doing. And it's a really impressive platform. I actually prefer this view of the NVIDIA platform. And now you can see at the bottom is where we have the hardware layer. Of course, we've got our individual GPUs, and then those go up into servers. But what I like to point out on the hardware side here is that NVIDIA's hardware can be found anywhere you need compute. I know we've got Azure here. They're one of our largest partners. All of our GPUs are found in all major clouds. If you're an on-prem shop, if you've got a data center on-prem, doesn't matter if you're a Dell shop, Lenovo shop, HPE, all of the major OEMs have systems with our GPUs in it. We've got the big GPUs that go in the cloud and the data center. Those are great for training AI models and running these large simulations. We've got mid-sized GPUs, and those are good for what we call the mid-edge. Think like a Walmart closet where they are doing AI on video feeds, or a power grid substation. And then we've got our small edge GPUs, the Jetson class GPUs. And if you're kind of like a tinkerer and a really nerdy engineer, then it's a really fun toy to play with, and I recommend checking that out. And so we've got this wide range of GPU. We make hardware, right? Hardware is what made NVIDIA famous. But software is what made us successful. It begins down at the CUDA programming language. Unless you're a brilliant mathematician like Andrew Larson is, you're probably not programming in CUDA. It's a very difficult language to program in. The good news is you don't have to, because NVIDIA has done a lot of hard work abstracting it away. You can come in where most people do at the developer toolkits level, where you're able to use the language that you know, the tools that you already know. C++, Python. If you're an AI researcher, you're going to be using TensorFlow and PyTorch, right? And so we've built all of these developer tools that make it incredibly easy for scientists and researchers to tap into the processing power of the GPU without worrying about low-level computer science. These developers then they take our tools and they build applications like Barracuda Virtual Reactor. So a lot of people, the business users, come in at the actual application layer where they're using, they're using these applications to move the business needle. Their business applications were developed using developer toolkits like our HPC SDK, TensorFlow, PyTorch. Those toolkits were accelerated by the NVIDIA CUDA library, which then runs on NVIDIA GPUs. That is why NVIDIA has become so dominant in the market today, and that is why competitors like Intel and AMD have had such a hard time catching up with us. It's not because they can't move electrons around as fast as we can. They actually can. It's because they don't have this fully built out, fully accelerated software stack that NVIDIA has been developing since the early 2000s. If you take away nothing from my talk today, just take away the understanding that software, not hardware, is the secret sauce of NVIDIA. One last look at our computing platform from a different level. This really shows the full stack innovation that we have at NVIDIA. We innovate at the chip level with our individual GPUs. We innovate on the system level with the ability to combine multiple GPUs together in our DGX Station, in our DGX, in our OEM servers. We innovate with the cloud providers like Azure, so that way they can scale this out to the hyperscale environment. We innovate on the software level with our SDKs and engines. We then help our ISVs like Barracuda take those software level optimizations, build it into their applications. And then we also really do a good job of nurturing and taking care of our developer ecosystem. We've got over 3 million developers on our platform. CUDA has been downloaded 30 million times. We actually have over 2,700 GPU accelerated applications and over 9,000 AI startups developing on the NVIDIA platform. If there are any Jim Cramer fans out here, this is the number that gets him the most excited. He says the 9,000 AI startups that are going to grow into the next generation of large companies, the fact that they're developing on the NVIDIA platform, he calls it a competitive moat for NVIDIA that the others just don't have. Now, I know this is an HPC conference, so I don't want to spend too much time talking about AI, but it is important if you want to have a good understanding of NVIDIA, and also there are some numbers that I think you're just going to find really interesting. And this middle chart, I'm not sure how well you can see it, but it's a log chart, and I love that I'm talking to engineers so you understand what a log chart is. And it's the compute requirements to train some of the more popular AI algorithms by year. Right there, we've got ResNet 50 taking about 10,000 petaflops to train, and that came out around 2017. Now, the blue line that you see here, those are kind of the older generation of AI neural networks, but this green line is a really interesting one. Those are the transformer-based models. Those are the types of models that are being used to solve large language models like the Megatron Turing NLG. It's got 530 billion parameters. But the really interesting thing is the trend. Again, keep in mind that this is a log graph, so that is a steeply rising exponential trend. And in just 2 years, these transformer-based AI models have grown by 275 times. The compute requirements to train them, 275x in just 2 years. If you've heard of Moore's Law, that kind of is what drove CPU development. It doubles about every 2 years. Moore's Law's got nothing on AI today. This is the reason why GPUs and not CPUs are what is driving the AI industry. Now, I mentioned earlier that we made it really easy for scientists and researchers to take advantage of the GPU. How easy do we make it? Does anybody here do any sort of data analysis using Python pandas? Raise your hand. Yeah, very popular framework. Runs only on the CPU. If you're just doing analysis on a data set that's a couple gigs, it's good enough. But if you start scaling out your data set to where you get into the dozens of gigs, hundreds of gigs, even terabytes, you're really going to hit that CPU bottleneck. It's going to take forever. That's why we came out with a package called Rapids, which moves the Python and scikit-learn tools over to the GPU. And I mean, it's this easy. Instead of import pandas as PD and then data frame equals pd.read CSV, import QDF, data frame equals qdf.read CSV. Syntactically similar. With just 2 lines of code, your code is now going to, or with 2 lines of code changes, your code will now run about 150x for those different pandas level workloads. And then I've got a couple different examples there. When you look, I went too far. No, I didn't. When you look at the entire AI pipeline, everything from ETL and data prep all the way through deployment, and you look at NVIDIA's compute platform, you realize that we've got tools that accelerate every portion of that AI platform. Now, you can still use CPUs for AI, but using a CPU for AI, that's like using a screwdriver to build a deck. Sure, with enough elbow grease and time, you can build a deck with a screwdriver. But we all know that that's not the right tool to use. You would rather use a power drill instead. Using a power drill, you can build a deck bigger, better, faster. Using CPUs for AI is like using a screwdriver to build a deck, and using GPUs is like using a power drill to build a deck. Now, the way we work with partners, not just in AI, but also in the HPC space, is we look at that pipeline, and we find all the areas here that they're using screwdrivers, and we drop in power drills. And that is why NVIDIA is so dominant here, is because we've got so many power drills, and we made it really easy to use them. Enough about AI. This is an HPC-driven conference. And so this is a nice look at some of the different pillars that NVIDIA is investing in, really driving the market in the HPC space. There's a new trend in HPC on moving compute to the edge. We've got these large scientific machines like the ITER in Europe for fusion research, or the Square Kilometer Array, where I mean, my God, they are collecting massive, massive data sets, and you can't pipe all that data back to the cloud. Even if you've got a data center a couple blocks away, I mean, moving that data is just infeasible. You need to bring compute to where the data are being collected, and so there's a huge trend now on moving HPC out to the edge. Quantum computing is an interesting one. I'll admit I'm kind of bearish on the whole quantum computing market right now, mostly because the hardware, I think, it has a long way to go. But the math of quantum computing is really well understood. And if you look at the language of quantum mechanics, it's all linear algebra. It's linear algebra and tensor products. That's a workload that our GPUs do really, really well. So we came out with a new library called cuQuantum that allows you to simulate these different quantum circuits and see how they would perform if and when we actually had a real quantum computer. So we're investing heavily in that. There are a couple really good GTC talks. And one of my favorite takeaways from those talks was one of the quantum researchers was saying that the best quantum computer available on the market today is actually an NVIDIA DGX because the actual quantum computers can do about 50 qubits, but using a DGX, you can actually simulate on the order of thousands of qubits. So that is what's driving the quantum computing market. Everybody here cares about simulation, so we're doing a lot of work with the simulation market. And then kind of the future where we're looking is where we're blending both simulation and high-performance computing with AI using things like physics-informed neural networks. If you're somebody like Andrew Larson and you're developing these HPC applications, you're going to live mostly in the HPC SDK. This is the toolkit that we give to our developers who are building applications for scientific computing. Of course, we've got different compilers. So if you've got a bunch of Fortran code or C++ code, you can move that over to the GPU. We've got the communication libraries like Nickel and NVSHMEM. Those are what you're going to use to scale your application out, not only to multiple GPUs, but then also to multiple servers as well, and you go multi-node. But what's really cool are the math libraries that we have right here. So we've got things like cuRAND for GPU-accelerated random number generation, really useful if you're doing Monte Carlo simulation. We've got cuFFT for fast Fourier transforms if you're doing any sort of signal processing. cuSolver for different algebraic solvers like AMGX. cuSparse for sparse matrix multiplications. We got cuBLAS for good old-fashioned linear algebra. And then cuTensor as well if you're doing any sort of tensor product type work. Now, when you look at the NVIDIA performance over in the HPC market, you see that in the last 6 years, we've grown 26 times faster. Now, that is a shocking number, so let's unpack that a little bit. We went back 6 years to our P100 GPU back in 2016, and we took a handful of some of the real heavy-hitting HPC applications like Milk and GROMACS that are run in the national labs, and then we kind of normalized, we took the average of their performance and normalized it, so that way we got a baseline for where we started 6 years ago. Now, in those 6 years, we've come out with 2 new GPUs. We came out with the Volta architecture, and then we came out with the Ampere architecture. So, if our performance were only due to innovation on the hardware level, you wouldn't see this curve up like that. You'd see kind of like a stair step. The reason you see a curve like that instead of a stair step is because we are not dependent only on hardware innovation at NVIDIA. We are also innovating on the software level as well. We have more software engineers than hardware engineers at NVIDIA, and their sole purpose is relentless optimization everywhere they can find it, and then we bake it in, and that's how we're able to get kind of a smooth trend up like that. Going back to Moore's Law, 6 years, if you're advancing at the pace of Moore's Law, is going to get you 8x performance improvement. We've been able to go 26x, again, because we innovate on the hardware and the software side. That is why we are in 71% of the top 500 most powerful supercomputers in the world. And then if you look at the top 10 supercomputers, we're in 7 out of 10 as well. Yesterday, somebody asked about what other applications you could run on a DGX, or if it was just a Barracuda appliance. It's not just Barracuda appliance. We've got over 2,700 applications you can run on not only a DGX, but just our software, our hardware in general. And they kind of transform all industries, everything from AI, media and entertainment, oil and gas, life sciences, you name it. Again, this wide breadth of applications that we're able to accelerate is one of the reasons why NVIDIA is so dominant in the market. Who here has heard of physics-informed neural networks? Pins, yeah. A couple people. It's relatively controversial, and you know, I have a physics background myself. I'll stand up here and say definitively, AI will never replace first principles physics. Repeat it one more time. AI will never replace first principles physics. That being said, it could be useful still, and we have this new trend, this new field called physics-informed neural networks, where we are able to blend neural networks with first principle physics. How does it work? You know, if you had a regular neural network, and let's take traditional AI. So let's say you had a picture of an animal, and you were trying to use AI to determine if that was a cat or a dog. You would take that image, you would feed it through your neural network. That last layer is called the output layer. It's a prediction layer. That's where it tells you, it makes a prediction, is this a cat or it's a dog? When you're training the AI algorithm, you know the answer because it's a labeled data set. So you take the prediction, you take the answer, you feed it through a loss function, and then you use something called stochastic gradient descent to nudge the neural network in the right direction, make it more and more accurate. So that's traditional AI. With physics-informed neural networks, instead of inputting an image, you input everything you can about the system you're trying to model. You input all the geometry of the system, mass flow, temperature, pressure, everything. You input it into this neural network, you shove it through. I should also say that it's used for solving differential equations. So if you've got an application like CFD, acoustics, heat transfer, this is the field that it's looking at. Okay, so you put all of the information in your system through a neural network. The output is a solution to that differential equation. And then the loss function that you send it through is where you get the physics-informed part. That's where you input your boundary conditions, your initial conditions, all of the laws of physics that you can, and then you use that loss function to nudge it in the right directions. That way you have a solution to the differential equation that was solved using AI but has been informed by the real physics. Now, again, this is never going to replace full fidelity CFD. It's never going to replace first principle physics, but it can be useful in certain areas where you don't have time to wait for full fidelity, or if you don't need full fidelity modeling. And one example is some work that we're doing with Siemens Energy. Now, they've got this large piece of equipment called a HRSG, a heat recovering steam generator. Are y'all familiar? Who's familiar with HRSGs? A couple people. Inside of a power plant, you burn natural gas or coal, and it converts water into steam. That steam turns a turbine, right? Yeah, that's a HRSG. Well, the device that captures that heat while water is converting into steam is called a heat recovering steam generator. These things are like 2 to 3 stories tall, and it's like this massive maze of pipes that are going everywhere, these metal pipes. I don't have to tell y'all that water is corrosive. Water at extreme temperature and pressure, like in these HRSGs, extremely corrosive. But the operating conditions inside of these HRSGs are just too extreme. You can't put a sensor in there. So how do you know what level of corrosion is happening inside of your HRSG? Well, today they have to shut the entire HRSG down, and then they use non-destructive testing to measure the corrosion inside of these pipes, because they do corrode. If you don't catch the corrosion in time at these extreme temperatures and pressures, they're going to explode. People are going to die. So it's very important work. You can't do full fidelity CFD on these HRSGs and do it at a rate where you're able to actually account for the daily operating conditions in this, because power is going to be ramping up and down depending on the needs of the electric grid. And so what Siemens Energy is doing is they're using physics-informed neural networks almost to act as a virtual sensor for this. They're able to input all of the conditions for this HRSG into a neural network, and they're able to use AI to simulate what it looks like inside of this HRSG unit. Is it a replacement for full fidelity CFD? No. But what they're able to do now that they've got this virtual sensor is, instead of shutting the HRSG down every 1 month to check for corrosion. They're now able to stretch out that time frame and shut it down every 3 or 4 months instead. I forgot the actual duration times, but by stretching out the amount of time where they have to shut it down to do the non-destructive testing, I mean, they're able to save hundreds of millions of dollars. And so this is a rapidly growing field in the conversion, combination of AI and HPC. I just kind of want to get it on your radar because it's really cool. It's still very much in the R&D space, but as the work continues, as more validation comes out, we do hope to see this move to the commercial space. I already talked a little bit about HPC at the edge. This is all about moving compute to these large scientific equipments where we're collecting large amounts of data like LIGO, square kilometer array, different other particle accelerators. You get it. I know we're a little bit behind on time, so I'm going to move through the next couple slides pretty quickly. Y'all have already been talked to a lot about the A100 and some of the different systems. We're not hardware salespeople at NVIDIA. We really just kind of want to evangelize our technology. So this is the A100. It's got 80 gigs of GPU memory. It's an absolute beast. Somebody yesterday asked about the comparison between the A100 and the last generation, the V100. So here's just showing for FP32 and Int8. Those are kind of the AI different workloads. We get about 20x performance improvement. Again, that's not only just because of hardware, but that's hardware and software innovation. For HPC applications like Barracuda that leverage FP64, we're seeing about a 2.5x performance improvement there. You can take 8 of these A100s, fully connect them with the technology we came out with called NVLink, and put them into a DGX A100. This is the most powerful single server in the world. It's got 640 gigs of GPU memory. It's an absolute beast. Really, the most difficult part about leveraging something like this is just keeping the beast fed. A lot of times companies will buy a DGX, and it's so fast at processing data, and they might have like some old 30 gig Ethernet port going into it instead of InfiniBand, and they're just not even able to keep it saturated. As soon as the data comes in, it's already processed. So it's an absolute beast. For the workstation users, which I understand a lot of Barracuda users are workstation users, we've got the DGX Station. That's got 4 of the GPUs fully connected with NVLink. It's water-cooled, so it's whisper quiet. And the really cool thing is that it's able to be plugged in under your desk. This guy is an absolute power hog. It draws about 10 kilowatts of power. To put that in perspective, your AC at home probably draws around 4 or 5 kilowatts. That's like twice your AC running, 24/7. This guy, on the next page I have the power draw, 1.5 kilowatts. That's like your microwave. So that's what lets you go and plug it in under your desk. It's really powerful. That's why it's been adopted by 6 out of the top 10 government institutions, 7 out of the top 10 U.S. hospitals. The number I'm really excited about is 10 out of the top 10 aerospace and defense companies. I'm excited about that because I just watched Maverick last weekend, so I'm feeling kind of hot on the aerospace industry. But sometimes we have customers that say, listen, we can't afford a DGX station. We certainly can't afford a DGX. We talked to IT. We've got an old Dell server, and he says it's got a PCIe slot that's in there. Like, could you do something for us? So we've got our GPUs. You can get a single GPU with the PCIe slot, pop it into one of your mainstream OEM servers that you have there. So we do have that option available. I mentioned earlier that our GPUs are kind of power hogs, right? Yeah, they do consume a lot of power. And if you look at where that power is going, not all of it's going to compute. A good chunk of that power is going to keeping that thing cool. And if you've ever taken a tour of a data center, I mean, you walk in and they just have these crazy powerful fans just blowing nonstop. Cooling is where a lot of the electricity is going in modern supercomputing systems. And so there's been this new trend around liquid cooling. And so NVIDIA decided to support that trend in the interest of the environment. And so now we also have baseboards with multiple GPUs available and even single PCIe ones where you can leverage liquid cooling. There are some even crazier supercomputing customers who are all about immersion cooling, which is where you take your server rack and you literally just dunk it in a tank of oil, And it sounds crazy, but we've got customers who are doing it, and the efficiency is just off the charts. And they've actually got a lot of data to show that the corrosion that's happening inside of these systems is happening at a lower rate inside of oil as opposed to inside of air. So if you ask me, I think it's controversial, but the future could be full immersion cooling, not liquid cooling. Grace. Not all applications can be run or should be run on a GPU. Not all applications are inherently parallel. Some of them are inherently serial, and so you need a CPU to process these applications. And for the last 15 years, these applications that can't really run on a GPU have been sitting by the wayside and just watching as the GPU's performance has been going through the roof, and they've just been kind of sitting there going at the pace of Moore's Law. And so we wanted to address this market and bring that NVIDIA level of innovation to the CPU market, which is why we partnered with ARM and came out with the Grace CPU. It's actually 2 CPUs on the same die. Each has about 72 cores. So we've got 144 ARM 9 cores on one single die. The memory bandwidth is amazing. We're using LPDDR5 memory as opposed to like HBM2. And you actually are familiar with this memory. This is what's found inside of your cell phone, right? It's incredibly fast, and the performance per watt of this memory type is just off the charts. And so you think, oh, well, why aren't more companies doing it? It's actually very difficult to design a chip that leverages this, and they also have to be, it has to be really close to the chip itself, which is why you see these two guys about 9 millimeters apart, because you can't have that kind of memory bandwidth greater than that. And so Grace is our answer to that long tail of HPC applications that don't run on GPUs because they're inherently serial, but we wanted to bring the NVIDIA level of innovation to the CPU market. So this is really exciting, and that's going to be coming out in the first half of next year. What's more exciting than Grace? Well, our next generation of GPUs is going to be called Hopper, right? And so we've got the A100, that's Ampere. Next generation is Hopper. We'll have the H100. The most exciting thing we're doing is combining them onto one single die. We've got our Grace CPU combined with our Hopper GPU, paying homage to Grace Hopper, who was, of course, one of the first female computer scientists. And now we have a CPU and a GPU on the same die, sharing fully coherent memory with 900 gigs per second of coherent memory. This is an absolute game changer. It really is hard to overstate just how cool it is to have a CPU tightly coupled with a GPU on the same die. This is the Grace Hopper Super Chip. This will also be available in the first half of 2023. CPU, GPU tightly coupled on the same die. That is the future of scientific computing, and that is where I'm going to leave you.